In this video, we're going to talk about inverse circular functions or inverse trig functions. Before we can talk about the trig functions, we really need to remember all the requirements and kind of the setup for finding an inverse function. So in order to have an inverse function, or I should say, it's possible to have an inverse function if we have a function that is one-to-one. One-to-one means basically one x to one y, right? So I don't have two x's that are the same and I don't have two y's that are the same. The way we check to see if a function is one-to-one is by using the line tests. So to check that each x corresponds to only one y, that's the same as the test for a function. That would be the vertical line test. To add to that, to make it one-to-one, we need to test that each y corresponds to only one x. And we use the horizontal line test to test for that. And it works in the exact same way as the vertical line test. So down here I have the graph for the sine. You could take your pen, right, and set it vertically anywhere along this function. It's only going to touch at one point. So it's definitely a function. But if I do the horizontal line test and I pass my pen horizontally, and given what we know about the sine function, that it is periodic and it repeats over and over again, this is definitely not one-to-one. So we kind of need to address that. So there is this process that we do even in algebra. If we don't have a function that's one-to-one, we can restrict the domain, or instead of looking at the whole function, we can look at just a piece of the function and allow our inverse to operate for just those x values. So for the sine function, we're going to use the restricted domain from negative pi over 2 to pi over 2. So in this graph, each tick mark is pi over 4. And so to go from negative pi over 2 to positive pi over 2, we're really talking about this piece of the graph right here in the center. Okay, so if we consider just that piece, not the whole curve, or the whole, I'm trying to say is, not the whole oscillating curve, just this piece of the curve. Now we could ask those same two questions, right? Does it pass the vertical line test? Definitely. Now that we've restricted the domain, does it pass the horizontal line test? Yes, yes it does. Okay, so if I just take this little piece of the sine function, I can say it's one-to-one. Okay, so that's really the starting point. In algebra, we talk a lot about how to find the inverse, so I'm just going to go through that quickly just so that you can get an idea of where these functions are coming from. I'm not going to do it for each one, but I am going to do it for the sine function. So to find the inverse, we first have to check that it's one-to-one. We just talked about that. The next step would be, if we have it written as a function, we would want to replace the f of x with a y. And then we're going to interchange x and y, which means everywhere where we have a y in the function, we're going to put an x. And everywhere where we have an x, we're going to put a y. And then we're going to solve for y. So to solve for y, I have to do the opposite operation of the sine. This is the inverse sine, right? So technically I would be taking the inverse sine of both sides. Kind of feels like cheating when you call it the inverse sine, but the inverse sine and the sine, when those are opposite operations, So they're going to cancel each other out. And that's going to leave us with y on this side and the inverse sine on the other side. Okay, so that's our inverse. So let me write this again for you in another way. Actually, let's give us a chance to graph the inverse sine. Okay, so here I have the sine function again, right? And I'll mark this. Here are some specific x values. We've already talked about the sine of x many times. Okay, so here are those values kind of right in that region. So we're going to kind of bring into play all the things that we know about inverses. So we talked about how to find the inverse. Now we're going to talk about some more of the graphing related ideas. So when I have an inverse function, the values for x and y, or the role of x and y, is reversed. So for the inverse sine, I'm going to put in the y value, which is the value I get from the sine, right? A real number, somewhere between -1 and 1. And when I put that into the inverse sine function, I get out of it the angle, either in radians or degrees. Right now we're going to work in radians. Okay, so basically the points that I have for the regular sine function are going to be reversed when I go to make the graph for the inverse sine. Okay, so some people like to fill these in first. If that's easier for you, that's fine, right? I'm going to get out the angles between -pi/2 and pi/2. And what's going to give me those angles is the value of the sine, right? So if I put in -1, I get -1 when I take the sine of either 3pi/2 or -pi/2. I'm going to get -√2/2 when I put in -pi/4. Right, that's the 45-degree angle. I'm going to get 0 when the angle is 0. I'm going to get the positive √2/2. One of the times I get that is when I have pi/4. And then I'm going to get 1 when I'm at that 90-degree angle at pi/2. Okay, so if we plot these points, right, now on our x-axis we want to use our real numbers, so this will be 1, 2, 3, etc. And on the y-axis we need the angles. So we're going to count by pi/4, just like we did on the graph of the sine on the x-axis. Okay, so at -1, I'm at -pi/2. At -√2/2, that's like -0.7. I'm at -pi/4. So right about here. I'm at 0, 0. Again, 0.7, I'm at pi/4. And at 1, I'm at pi/2. So I get a curve that sort of looks like this. Okay, one more fact about inverses is that the shape that we get here should be the shape of the original graph, but reflected over the line y = x, which is this diagonal line down the center, right? I'm not going to draw that because I don't want it to be confusing, but if we put these two curves together, we should see that they're reflections of each other in that way. All right, the domain here, that's the values for the sine, so they're going to go from -1 to 1. And the range, because we're using that restricted domain for the sine, the range is going to be from -pi/2 to pi/2. Okay, so I thought we would do that for sine, cosine, and tangent so that you could see where all three of these graphs come from. So let's do the cosine next. Here's the traditional graph of the cosine. Again, we are counting by pi over 4 each time. Okay, so that we have the same problem here. It's really the same curve, just kind of shifted over. It definitely passes the vertical line test, but it does not pass the horizontal line test. So we're going to restrict the domain. For the cosine, we usually restrict it between 0 and pi. The logic for that is we're choosing a region on the curve that shows the y values going from -1 to 1, or in this case from 1 to -1. Okay, so again, here are all the angles in radians. Here are all the values for the cosine. So when we go to make the inverse cosine, all those relationships of inverses are going to come into play. So again, the values that we would normally get out of the cosine are going to act as the x values. And then the y values that we get out would be the angles that create these values for the cosine. So it's an angle of 0 that gives us a 1 when we take the cosine. Cosine of pi over 4 gives us square root of 2 over 2. Cosine of 90 degrees, or pi over 2. And on all honesty, in my head, I'm thinking about, right, the unit circle when I do these, right? So I'm thinking about where those values come from when I use my unit circle. Negative square root of 2 over 2 is going to be past the 90-degree mark, so 3 pi over 4. And then -1 would be at pi. Okay, so again, when we set up the x-axis is the value of the cosine, so it's just going to be regular real numbers. The y-axis is the angle, so we're going to set it up in radians, jumping by pi over 4. Should be a 4. Okay, so we've got the point 1, 0. Square root of 2 over 2, remember we said that's about 0.7, is at pi over 4. 0, pi over 2. Negative 0.7, 3 pi over 4. And then -1 pi. And again, this would be a curve that is a reflection of the cosine curve with that restricted domain over the line y equals x. Okay, the domain here again is going from -1 to 1. That's normally the range for the cosine. These are reversed, right? And then the range is going to be our restricted domain from 0 to pi. All right, let's look at the tangent. So here's the graph for the tangent. We also have some asymptotes in here that were kind of hard to type in, so I'll add them in right now. Okay, so remember the tangent is the sine over the cosine. So any place where the cosine would be 0, we can't divide by 0, so we have a break in the graph where we put these asymptotes. That's where it's undefined. So there's going to be at negative pi over 2 and pi over 2. And so just like for all the others, we are, right, This graph is a function. It passes the vertical line test, but because it's repeating, it does not pass the horizontal line test. So the restricted domain we use for the tangent is just one period, which for the tangent is from negative pi over 2 to pi over 2. So this whole piece right here. Okay, and just that piece is 1 to 1. So the inverse tangent will be the reflection of that, and we'll kind of reverse these coordinates. All right, when we do the reflection, right, anything that's vertical becomes horizontal. So these vertical asymptotes will become horizontal asymptotes when we draw the inverse tangent. And so I've kind of labeled them that way just to make it easier for us to think about. But these will be the values we get for the tangent. We're going to use -1, 0, and 1. We said that the tangent is undefined when we put in an angle like negative pi over 2 and pi over 2. So for the inverse tangent, what happens is really the opposite of what happens in the tangent. Let me go back. As we get closer to pi over 2, as the x value gets closer to pi over 2, the y value is shooting up to infinity on the right, and then on this side shooting down to negative infinity. So for the inverse tangent, as we're going towards negative infinity, the y value is going to approach negative pi over 2. And as we're going to positive infinity, it's going to approach pi over 2. Okay, but to get -1, we used negative pi over 4 to get that. The tangent of 0 is 0, and the tangent of pi over 4 is 1. So if we graph that, same thing's true here, right? These are real numbers, and then these are angles. So we've got at -1, we're at negative pi over 4, 0, 0, and 1 pi over 4. Okay, and then just like we said earlier, we're going to have a horizontal asymptote at pi over 2 and at negative pi over 2. We could definitely plot more points if we needed to, but this curve should sort of look like this. The tangent curve has always looked like x cubed to me in a way, so the inverse tangent looks a lot like the cube root. Okay, the domain is going to go from negative infinity to infinity. And the range is that restricted domain that we started with. Because of the asymptotes, we don't actually hit negative pi over 2 and pi over 2, so we're using parentheses. All right, so we took some time to talk about where these functions come from, what their graphs look like. Now let's talk about using them to solve problems. So we'll do a couple of these together. We'll start with this one. These are from your book. We want to calculate the arc sine or the inverse sine of negative square root of 3 over 2. So basically that means we're looking for the angle whose sine value for the sine is negative square root of 3 over 2. This arc sine, I just wanted to give you a couple that are written both ways, is the same as the sine inverse. These are interchangeable. All right, so let me bring in my unit circle to help us out. So for what values, okay, I guess we should say, right, Because we restricted the domain for the sine, remember our, I want to say restricted domain, but for the sine inverse is also the range, so I'm not going to label it, but we're trying to find an angle between negative pi over 2 and pi over 2. So in terms of the unit circle, I don't have the whole thing drawn here, but that would be quadrant 4 and quadrant 1, right? Anywhere in here. Where would it be negative square root of 3 over 2 for the sine? The sine is the y value. This is where it is positive square root of 3 over 2. That's at 60 degrees or pi over 3. So it would be 60 degrees below the x-axis, right? Or negative pi over 3. Okay. And if you wanted to prove that for yourself, you could just, you could even use your calculator, right? But we're trying to do some of this in our head with our unit circle as our helper. But if I took the sine of negative pi over 3, I should get negative square root of 3 over 2, right? That's sort of how I could check that I did that correctly. All right, let's try another one. How about the secant, the inverse secant of 1? So this is the same as 1 over the inverse cosine of 1. Oh, sorry, I did that wrong. Just kidding. I always mess this up. Actually, this is the cosine inverse of, right, I would take the reciprocal of this value. It's kind of tricky to think about when it's just 1. But if it were 2 here, it would be the cosine inverse of 1 over 2, right? And that kind of makes sense if you think of the value of the secant is 1 over the value of the cosine. And this is the value, right, that we're manipulating. Okay, so the cosine inverse of 1 here's where we would pull out our unit circle, right? Remember the restricted domain or the range for the cosine inverse is going to be between 0 and pi. So I want to go from here all the way over here and think about any place where the cosine would be 1. So I have this written backwards. Okay, so this would be where the cosine is 1. So that's at 0 radians. Okay, and really that's all there is to it. I'll add radians since we're talking about radians here. Again, you could do these in either degrees or radians, but right now we're just going to use radians. Okay, here's another one. This time we have two trig functions together. So anytime we have that, we want to kind of work from the inside out. So I have the arc cosine of 3 over 4. So it may be good to draw a picture of this, right? And again, we're dealing with cosine, same as cosine inverse if you prefer that. So we're working between 0 and pi. So let's draw a picture of that. So if the value of the cosine is positive, that tells us that we're in quadrant 1. Right? It could be quadrant 1 or it could be quadrant 2 to be in 0 to pi. But if it's a positive number, the cosine is going to be positive here. It's going to be negative here. So we know it's in quadrant 1. And then we could draw a triangle. Call this angle X. whose cosine is 3/4. So adjacent over hypotenuse. And then now that we've drawn a picture of this angle, we want to take the tangent of this angle. So we really need this other side of the triangle, so let's solve for it. Let's call it b, okay? So 3 squared plus b squared equals 4 squared. So that's 9 plus b squared equals 16. If I subtract 9, I'll have b squared equals 7. So b must be the square root of 7. Positive or negative? We're in quadrant 1, so it's positive. Okay, so now the way we've drawn this, we've made it into a picture where we've shown the value of x. We don't know what the angle is, but that's okay. We don't need to, because really we're asked to find the tangent of that angle. Remember, tangent is opposite over adjacent, so this would be the square root of 7/3. Okay, and you don't have to write this part. I was just trying to give us a transition, but this would be our final answer. All right, how about one more? So this would kind of be worked out in the same way, but now we're going to bring in an identity along with. Okay, so we have the cosine of 2 times the arctangent of 4/3. And we want to use the double angle formula because it's cosine of 2 times the angle, right? Think of this right here is our angle, right? All right, so that's going to be equal to 2 times the cosine squared of, you can leave it as arc, I'll leave it as arctangent. You could make it into tangent inverse if you like that better. Minus 1. Okay, so let's find the value of this, right? Maybe it'd be better to write it as cosine of the arctangent of 4/3 squared. That might be easier to think about. Let's draw a triangle for this. Okay, we're dealing with the tangent, which means we're working between -pi/2 and pi/2 as our restricted domain. So that's quadrant 4 and quadrant 1. So then we want to ask ourselves, oh, excuse me, where is the value of the tangent positive? I think we can agree that's going to be in quadrant 1, where both sine and cosine are positive. So if we draw a triangle, okay, let's call it x, just to have something to name it. The tangent of that angle x is 4/3. So that means that the opposite over the adjacent is 4/3. And we want to find the cosine of that angle. So again, if you need to, this one is a Pythagorean triple. Oops, I almost wrote the answer. Okay, so I'll go ahead and calculate it out, but you might already know this one. It's kind of a famous one. 9 and 16 make 25. Okay, and the hypotenuse is always positive. So I take the square root of both sides. So I'm going to get 5. Okay, so now we want to take the cosine of this angle, arctangent of 4/3. The cosine of x would be adjacent over hypotenuse, so 3/5. And then we're going to put it into this double angle formula, right? So the cosine of our angle is 3/5. So we're going to square that, multiply by 2, and subtract 1. So that ends up being 2 times 9/25 minus 1. So that's like 18/25 minus 25/25. 18 minus 25 would be negative 7/25. All right, well, I hope this gave you a little bit of an idea of how to work with inverse sine and inverse cosine. We want to get comfortable with these mainly because trig is going to become far more useful if we can solve for these angles. That's what we're going to use it for. So in the next video, we'll be solving equations, and we'll use these as a tool. So this is just a good explanation of our tool today. All right, well, good luck, and we'll see you in the next video.